Engineers are transforming the way we power the world, replacing old carbon-intensive technologies with clean, renewable sources of energy. And the speed of change is unprecedented.
The energy transition that's happening at the moment is a complete paradigm shift. Rather than big, centralized thermal generation, burning coal, burning oil, burning gas, we're now decentralized, solar, PV, all over the place.
Wind and solar, which are now commonplace, really, they were almost non-existent. They were just a minority thing 20 years ago.
But the meteoric rise of renewable energy has consequences for our electricity supply. While coal and gas-fired power stations can generate electricity whenever you need it, renewables are intermittent by nature. So we need a backup plan for when the wind stops or the sun goes down.
So the solution to intermittent power provided by renewable energy is to provide power quickly using energy storage devices.
Teams of engineers are searching for ways to store green energy with mechanical batteries, so that when extra power is needed, these devices can bridge the gap, instead of relying on more polluting sources of electricity.
The ultimate solution really is to have much, much more energy storage built into the grid, so that at times when there's a surplus of energy, such as when the wind's blowing very strongly and the sun is also shining, one can save energy and store it.
We're going to need a lot of innovation for new technologies to be able to store this energy so that renewable can generate and we can utilize that when the grid needs it, when the demand is.
The success of the green energy revolution depends on these engineers and their marvelous machines.
If we were to keep increasing the amount of renewables on the grid, but we didn't implement energy storage at the same time, our grids will start to get unstable. We'll start to have more and more frequently periods where power wasn't available to us.
Already, there are ominous signs of what a future might look like without enough energy storage. In August 2020, California was about to experience a glimpse of this potentially devastating future. The most extreme heat wave of recent decades was wreaking havoc on the western United States. Elliot Mainzer, CEO of the California Independent System Operator, was paying close attention to the weather.
August of 2020 saw a heating event that hadn't been seen in many, many years. It was simultaneously extremely hot in just about every part of the western United States, with temperatures well into the 100 degrees in California and in many parts of the region. It was what we've referred to as a heat dome that sat over basically the entire western United States.
Then, sweltering Californians were suddenly confronted with another rare event. From 6:30 p.m. on the 14th of August, their electricity was suddenly cut off.
It was the first time that California had experienced any types of rotating outages from a shortage of electricity in 20 years.
This shortage may seem surprising, as California has invested heavily in green energy generation. In fact, during the spring, they have so much solar power, they export it to neighboring states.
California is, first and foremost, very blessed to have a very significant solar energy resource. We have over 15,000 megawatts of solar operating on the high voltage grid, and also behind the meter, a lot of rooftop solar in California.
So, with enough solar panels to power nearly every household, why did California run out of electricity during a heat wave, when there was plenty of sunshine? The answer was all in the timing. As the sun went down, power-hungry air conditioning systems stayed on, so the supply of solar power fell while demand for electricity remained high. In the evenings, California often imports surplus electricity from neighbors, but this time, they couldn't rely on other states.
It was so hot in these other areas that they needed that electricity for their own customers and didn't have as much surplus to sell into California. And that put us into a really stressed situation during a time of the day when we simply don't have enough capability to ride through those types of conditions.
Planned energy shutdowns were the only solution. The result was hours of blackouts for 2 days, affecting nearly 500,000 people. If California could have stored more of the solar power generated during the day to use in the evening, the crisis could have been averted. When solar panels produce more electricity than is being used by homes and businesses, the surplus energy can instead charge batteries. Then, when solar panels are generating less power than is needed, the batteries can discharge their electricity to the grid, making sure there's always enough for everyone. Since the blackouts, Elliott has been investing heavily in batteries, but that won't be enough.
Today, the primary battery storage resource on our grid are 4-hour lithium-ion batteries. And they are going to continue to grow in scale and scope here in California. But they are not going to be sufficient on their own to carry all of the load of the transformation.
The state's capacity has increased tenfold to 2.5 gigawatts. But Los Angeles alone uses 6.5 gigawatts. And lithium batteries can't provide power for long enough to get through the night.
We are going to need longer duration storage. You want a diversity of supply. You don't want to have such a dependence on a single technology.
California is ahead of the curve. But all over the world, renewable energy is growing fast. Without a revolution in energy storage, the world faces mass blackouts. Electricity grids need energy storage that is cheaper than fossil fuels to be competitive. They need them to be long-lasting to provide power for days or even weeks. They must also be fast-reacting to respond rapidly when the demand spikes. But above all, they need to store vast amounts of energy to help the world switch over to renewables. One nation that's attempting to build a giant energy storage system is Switzerland. The Alpine country boasts over 600 hydroelectric plants. But this know-how in capturing energy from water is being taken to the next level here at Limon Dam to build a huge water-powered gravity battery known as a pumped storage plant. Deep inside the mountain, a turbine hall will connect Dam Limon to Lake Mut, 1.5 miles above sea level. A 2,000 feet difference in height between the two reservoirs will allow them to store energy. When there's surplus electricity available, the gravity battery can be charged by pumping vast amounts of water upstream to fill up the lake. The gravitational potential energy of the water in the upper lake can be released to generate electricity whenever it's needed. The pumps will then rotate in the opposite direction, acting as turbines, generating electricity and sending it to the grid. The engineers aim to generate enough electricity for the Limon Dam to supply up to 1 million Swiss homes at peak power. In January 2010, energy company Axpo started building one of the biggest batteries in the world. The project would be one of the most ambitious engineering feats ever attempted at such a high altitude. Overseeing the construction of this vast pumped storage plant was project manager Martin Hussler.
This was a huge work which has to be done with a maximum of 700 people here, and they work together. It was a huge construction site.
With no road access permitted to this protected part of the Alps, the engineers had to find a solution to lift all the necessary building equipment to the top of the mountain. So the team built 2 cable systems, each spanning just under a mile, that could lift the equipment at 10 miles per hour.
We had 2 aerial cableways. The first cableway has a capacity of 40 tons, and the second cableway has a capacity of 30 tons. And all the machinery was taken by the aerial cableways to the Lake Limmen and to the Lake Mut.
Next, they had to dig through a wall of rock to the center of the mountain. Boring machines excavated a 2-mile-long access tunnel through which the team could bring the equipment from the top of the cableway. Then the team used explosives to excavate the caverns before collecting up the rubble to make concrete for the project.
The rocks were excavated from the caverns, were crushed and prepared for the concreting, because this was the main material for the concreting from the liner in the cavern.
The builders produced enough concrete to build 700 suburban homes, and even more concrete was needed for the dams.
Most of this crushed stone was transported with the aerial cableway to the Lake Mut and was used for concreting of the gravity dam.
This structure will be the longest in Switzerland, and it will triple the capacity of the lake.
The altitude of the dam is 2,500 meters approximately, and this is the highest in Europe. So this was also a logistical challenge.
The team had to excavate 2 main caverns out of solid rock. A powerhouse cavern for turbines and generators, and a second cavern to house the transformers. Then they had to line both caverns with concrete and build arches to reinforce the structure to withstand the weight of the mountain above them.
The whole plant, with all the tunnels, was approximately 400,000 cubic meters. And as a comparison, our main cavern is approximately 15% larger than the interior volume of the St. Paul's Cathedral in London.
The cavern was finally ready for the transformers to be installed, but there was an issue. They weighed over 200 tons, which was too heavy for the cableway. The solution was for the engineers to fit a funicular rail system into an access tunnel, which could lift up to 220 tons. Then the team built 4 pits for the turbine and generator units. These would weigh too much for even the funicular, so instead they meticulously assembled them in situ. First came the enormous pump turbines. As these blades rotate, they transform the kinetic energy of the water into rotational energy.
The runner has a power of 250 megawatts, and its design has 9 blades. And in pumping operation, the runner turns in this direction, and the flow goes through these channels and goes to the Lake Mut to store energy. This allows to fill Lake Mut in about 40 hours. In turbine mode, the water is coming from the Lake Mut, going through these channels, and the water flows through this channel out and is going to the Lake Limmen. And for all 4 runners, we have a total discharge of 160 cubic meters per second.
That's enough to fill 4 Olympic swimming pools every minute. Finally, the team assembled the generators, each weighing 360 tons. To generate power, operators open the valves and water flows into the turbines. The generators convert the rotational energy into electrical energy. The Linth-Liemern pumped storage site took 10 years to build, and it came online in 2020.
The feeling after we have successfully done the project was great, of course, because this is a huge project. It takes a long time. to fulfill all these requirements, and we are still working on it.
It can now provide a massive 1 gigawatt of power on demand, the equivalent of a typical nuclear power plant.
It is very important to have this pump storage power plant because we are able to store a large amount of excess electrical energy produced by solar and wind power.
The Lehman Energy Storage Plant can provide Switzerland with green power even when the sun or wind drops.